Let me begin my talk with a famous Chinese proverb. This is one of my favorite proverbs. And this proverb is about teaching and the learning. And this is from the perspective or the point of view of a learner, that's a student. And it goes like this. Tell me, I will forget. Show me, I will remember. Involve me, I will understand. To these three statements, I would like to add one more statement. That statement is motivate me, I will involve. Now the proverb will read like this. Tell me, I will forget. Show me, I will remember. Motivate me, I will involve. Involve me, I will understand. So according to this proverb, good teaching is all about motivating the students, involving them in the learning process, thereby making them understand the scientific concepts not only completely but also correctly. So, if I want to make you understand all the difficult and abstract concepts I will be teaching today and tomorrow, I have to motivate you and get you involved in the learning process. Conversely, if you want to really understand and appreciate all the concepts I will be discussing today and tomorrow, you must be mentally prepared to get involved in the learning process. And I have prepared the slides in such a way that there is provision for you to get involved in the learning process. So, my humble request is please take this webinar seriously and get involved in the learning process. And if you are prepared to do this, I promise you a really rewarding learning experience. This is a promise from my side. I can give you a really rewarding learning experience. And this is my first presentation, the symmetry element and the symmetry operations, the part one. And this presentation deals with identity element E and the proper rotation axis, the CN. See, group theory is a branch of the mathematical field of algebra. The foundation for the group theory was laid by the work of the French mathematicians Évariste Galois, 1811 to 1832, just 21 years, 20 or 21 years in the early 19th century. Group theory is one of the most important abstract theories in algebra. I expect you to know the meaning of the term abstract. So, I'm giving the meaning. The abstract meaning existing in thought or as an idea, but not having a physical or concrete existence. A typical example of a theory or a concept or a topic which is abstract in nature is mathematics. Then quantum mechanics is another abstract topic. So is group theory and chemistry. And whenever a theory or concept is abstract in nature, it's extremely difficult to learn the topic and even more difficult to teach these topics to others. There's a reason why quantum mechanics and group theory and chemistry are regarded as two of the most difficult topics in chemistry, not only in India, but all over the world. Now, before I proceed with the discussion of the group theory, I would like to say a few words about the man who is behind the group theory, the man who is behind this particular webinar, the genius called the Évariste Galois. Évariste Galois was a French mathematician and a political activist. In algebra, a particular problem remained unsolved for more than 350 years. This problem was finding the necessary and sufficient condition for a polynomial to be solved by radical. This is a problem. While still in his teens, Évariste Galois was able to determine the necessary and sufficient condition for a polynomial to be solved by radical. So he was a born genius. He is known for his work on theory of equations, group theory, and Galois theory. He was born in 1811. He died in 1832 at a very young age of 20 years. His short life ended tragically in a duel over possibly a cock with a woman. A duel is a contest with deadly weapons arranged between two people in order to settle a point of honor in France. And probably he had a premonition that he might die in the duel, so he spent the previous night writing down some of his most important mathematical ideas, including the group theory. Till then, he had never the practice of writing down his ideas. Only on the previous night, he wrote down the most of the important mathematical ideas, which included the group theory. These papers were discovered 14 years later and now recognized as the work of a genius. Now, the group theory has many important applications in the fields of physics, chemistry, and material science. Some important applications of the group theory in the field of chemistry include: one, the prediction of the polarity of the molecule. We can predict whether a particular molecule is polar or non-polar. Then prediction of the chirality of the molecule, prediction of the optical activity of the molecule. Then derivation of symmetry selection rule for electronic, vibrational, and Raman spectra. Prediction of IR Raman active vibrational modes in molecules. Then construction of the molecular orbitals in compounds. Then prediction of atomic orbitals involved in various types of hybrid orbitals like tetrahedral, trigonal planar, square planar, trigonal bipyramidal, octahedral, etc. Then simplification of quantum mechanical calculation. Example, simplification of Huckel's molecular orbital calculations. And finally, the construction of energy level diagrams of coordination complexes in Ligand field theory. You'll find all these applications in the postgraduate syllabus of the group theory and chemistry. Now, before I proceed to the real discussion of the group theory, I want to make certain things very clear at the outset. Be patient and study group theory. Since the group theory isn't the abstract topic, you won't be able to grasp the nuances of the concepts in the first reading. So you need a lot of patience to understand and appreciate group theory. Then two, you remember that once you get familiar with the basics, you'll find group theory very interesting and quite easy. So familiarity and the fluency with the basic concepts in the group theory is what is needed to make the study of the group theory interesting and quite easy. And the more you learn, the easier it will become. And unfortunately, many participants are going to miss these introductory topics, which are going to be the very, very important for understanding and appreciating the group theory. See, I'll try to make this webinar as interactive as possible. But in the classroom situation, it's very, very easy for me to make the session completely interactive. Here, there are certain limitations. But within these limitations, I will try to make this as interactive as possible. The concept fundamental to the application of the group theory to problems in chemistry is. I can't say you tell me because you cannot tell me. So I'll tell you, you decide what is the concept fundamental to application. You think an answer for this question. That is symmetry of the molecule or the molecular symmetry. But symmetry of molecule is a concept which is fundamental to the application of the group theory to problems in chemistry. Now, what is symmetry? I will explain the concept of the symmetry now. You consider these objects. This is a sphere, this is a cube, this is a rectangular slab, this is a stone. Now I ask you, I tell you, then I ask you to classify these objects as symmetrical and not symmetrical. You'll immediately say that the sphere is the symmetrical. The cube is symmetrical, the rectangular slab is symmetrical, but the stone is not symmetrical. It's your instinct which makes you tell me that the sphere, cube, and rectangular slab are symmetrical objects, whereas the stone is not symmetrical. Now I ask you to compare the symmetries of the cube and the rectangular slab and tell me which is more symmetrical. Without hesitation, you will say that the cube is more symmetrical than the rectangular slab. Now, if I ask you to compare the sphere and the cube, you will have the ready answer. The sphere is more symmetrical than the cube. So, sphere is more symmetrical than the cube, and the cube is more symmetrical than the rectangular slab. You can very easily answer these questions. But if I press further and ask you to tell me, why did you say that the cube is more symmetrical than the rectangular slab and the sphere is more symmetrical than the cube, then you will be at a loss of words. You won't be able to explain your instinctive feelings into words. It's not that easy to explain these facts. That is, cube is more symmetrical than rectangular slab and the sphere is more. In the day-to-day language, in the non-geometric sense or in everyday language, symmetry is associated with regularity in form. You can see that there's a regularity in form. Then the pleasing proportions. Then the harmonious arrangement and the sense of beauty. In the geometric sense, however, the symmetry can be defined more precisely in terms of what are called the symmetry operations and the symmetry element. So in the geometric sense, symmetry can be defined more precisely in terms of symmetry operations and the symmetry elements. Now, before I explain what is meant by a symmetry operation, let me explain what is an operation itself. See, an operation is any movement of the molecule or an object. Operation is any movement of a molecule or an object. So rotation about an axis is an operation. Now look at the video window. I'm going to show a molecule. This is a water molecule. This water molecule can be rotated about 3 mutually perpendicular axes. This is one axis. I can rotate it about this, or I can rotate it about this axis. Then it will come here, or about this 3. So this can be rotated about 3 mutually perpendicular axes. In fact, any molecule can be rotated about 3 mutually perpendicular axes. So all these rotations are operations, and these operations may be diagrammatically represented like this. So these 3 rotations can be represented like that. Likewise, a molecule can be reflected in a plane. Say this is a water molecule. This can be reflected about this plane, or this plane, or about this plane. 3 mutually perpendicular planes. And I will show just one of these planes in the diagram. Then inversion about a point. The inversion is nothing but reflection about a point. Then the translation. See, translation is the movement which changes the position of the molecule or object. Suppose I hold the molecule like this. I change the position. This movement is called the translation motion. So the operations are rotation, reflection, inversion, the translation, etc. Now, what is symmetry operation? Now, an operation will be called a symmetry operation only if it satisfies a particular condition. A symmetry operation is a movement of a molecule such that the resulting configuration is indistinguishable from the original. See, suppose I hold this, look at this. I hold this molecule, I rotate it about this axis through 180 degree. Then I get this configuration. This is diagrammatically represented like this. On the other hand, if I rotate the same molecule through 90 degree, this will come here. This bond will be pointing towards me. This will be pointing away from me. This can be diagrammatically represented like this. This is a, what do you call them, wedged bond, which is pointing towards me. There is a hashed wedge or the dotted wedge, which is pointing away from you. Now, these are the original configurations. These are the resulting configurations. Now, of these two configurations, one configuration is indistinguishable. The other is distinguishable. See, indistinguishable means you cannot differentiate. Distinguishable means we can differentiate it. Now you tell me or you decide whether this is distinguishable or indistinguishable. This is indistinguishable. So this is a symmetry operation. What about this? These two are clearly distinguishable. So this is not a symmetry operation. And we will be using the two terms, indistinguishable and distinguishable, quite frequently in the further discussions. So when I use these terms, you must know what I really might mean by these terms. Now, look at these. You tell me whether this is a symmetry operation. When you rotate it about this axis, these two will interchange. So this is a symmetry operation. What about this? These two hydrogen atoms will come here. So this is not a symmetry operation. Likewise, this is also not a symmetry operation. So the point I want to emphasize is that any molecule can be rotated about three mutually perpendicular directions. But all these rotation need not necessarily be then what? The symmetry operations. So the symmetry operation will give an indistinguishable the configuration. Now, during any symmetry operation, at least one point in the molecule should remain unchanged. At least one point in the molecule should remain unchanged. This point is the center of gravity of the molecule. So during any symmetry operation, at least one point should remain unchanged. This point is the center of gravity of the molecule. So only those operations which will leave the center of gravity of the molecule unchanged can be symmetry operations. During translation, there is a bodily movement from one point to another. The center of gravity of the molecule is changed. So the conclusion is the molecule should never be translated during symmetry operation. In other words, the translation can never be a symmetry operation. A rotation can be a symmetry operation, reflection can be a symmetry operation, inversion can be a symmetry operation, but translation can never be a symmetry operation. Now, symmetry element. A symmetry operation is a movement of the molecule. What a symmetry element is a geometric entity such as a line, a plane, or a point about which one can perform an operation of rotation, reflection, or inversion. So a symmetry element is a geometric entity. And the geometric entities are line, plane, or a point about which you can perform an operation of rotation, reflection, or inversion. A symmetry operation will transform a molecule into an equivalent or identical configuration. An equivalent or identical configuration. So let me explain what I mean by equivalent and identical configuration. Suppose this is a water molecule. I label the two hydrogen atoms as 1 and the 2. I rotate it through 180 degree. I get this configuration. Now, when this is rotated, this will become 2, this will become 1. And give it another rotation. This becomes 1 now, this becomes the 2. Now, let me label these three configurations as 1, 2, and 3. Now you consider the configuration 1, 2, and 3. Decide whether these configurations are distinguishable or indistinguishable. They are indistinguishable. Therefore, this operation is a symmetry operation. Now, the symmetry element is an imaginary line, and the symmetry operation is a rotation about this axis through 180 degree. Now, you compare the configuration 1 and 3. The configuration 1, the hydrogen labeled 1 is on the left, and in the configuration 3 also, hydrogen label 1 is on the left. Hydrogen label 2 is on the right in the configuration 1. In the configuration 3 also. So, these two configurations are, you tell me or decide, identical or equivalent. They are identical. They are indistinguishable and also identical. On the other hand, you compare these two. 1 here, 2 here. They are indistinguishable, of course, but they are not identical, they are equivalent. Likewise, 2 and 3 are also equivalent. So, I want you to appreciate the difference between the equivalent configuration and identical configuration, because these concepts are going to be used extensively in explaining several difficult concepts. Now, during any symmetry operation, the center of gravity of the molecule should remain unchanged. We have just seen that during any symmetry operation, the center of gravity of the molecule should remain unchanged. So, only those operations which will leave the center of gravity of the molecule unchanged can be symmetry operations. In nature, this is a very important fact. There are only 5 basic operations which will leave the center of gravity of the molecule unchanged. In other words, there are only 5 symmetry operations in nature. If you want to note down, please note down that there are only 5 symmetry operations in nature. They are identity E, then proper rotation axis Cn, mirror plane sigma, the inversion center I, and the improper rotation axis Sn. So these are the 5 symmetry operations present in the nature. Identity, proper rotation axis, mirror plane, inversion center, improper rotation axis Sn. Now the 5 symmetry operations are associated with the 5 symmetry elements. These 5 symmetry operations and the 5 symmetry elements are presented in this table. Identity. Symmetry operation is doing nothing. Suppose I have the water molecule like this. I don't do anything with this water molecule. Then I say that I have performed an identity operation. Doing nothing is identity. Then proper rotation axis, rotation about the axis through some angle. Mirror plane or the plane of symmetry sigma, reflection about the plane. Then inversion center or the center of symmetry I. The symmetry operation is inversion, or inversion is reflection about a point. Then improper rotation axis Sn, rotation about the axis through some angle, followed by a reflection in a plane perpendicular to the rotation axis. Now, we shall discuss these 5 symmetry operations and the elements one by one in some detail, because a clear understanding of the properties of these symmetry elements and the symmetry operations is absolutely essential for applying the group theory to problems in the chemistry. Identity. This operation does nothing. It is the simplest of all the symmetry operations. This is the only element or operation possessed by all molecules. Both the symmetry element and the symmetry operation are denoted by the same symbol E. Both the symmetry element and the symmetry operation denoted by the same symbol E. So, we use symbols for the symmetry element and the symmetry operation. In the case of identity, the same symbol E is used for the symmetry element and the symmetry operation. If this operation is carried out n times, it is denoted as e to the power n, where n is 1, 2, 3, 4, etc. And e to the power n is e, whether n is odd or even. Then e to the power 2 is e performed 2 times, e and e, which is identity. The identity E can generate only one operation, namely E. This is a very, very important fact. If you want, you can jot that down. The identity element E can generate only one operation, namely E. Then proper rotation axis, the Cn. If the rotation of a molecule about an axis through some angle results in the configuration which is indistinguishable from the original, then the molecule is said to possess a proper rotation axis. You already know that. It is denoted by the symbol Cn, and the C stands for cyclic. N is equal to 360 by theta, where theta is the angle through which the molecule is rotated. Cn is called n-fold rotation axis, and n is the order of the axis. So Cn, C cyclic, n 360 by theta, Cn called the n-fold rotation axis. Water molecule has to be rotated through 180 degree about this axis. So the symmetry axis is 360 degree by 180, which is equal to two-fold rotation axis, and denoted as the C2. Now, the angle of rotation, order, and the symbols of some proper rotation axis are present in this table. Degree, theta in degree, n is equal to 360 by theta, then symbol of the proper rotation axis. 180, this is 2, this is C2. This is 120, this is 3, this is C3. Then, if the order is 4, then the angle will be 90, this will be C4, and if it's a C5, you calculate, work out. N is equal to 5. What about the angle? That will be 72. Be careful with the 72. Then if it is 60, this is 6. This is quite an easy table which you can very easily remember. Now we come to the real, the abstract, concepts in group theory, the real difficult part, the identifying the proper rotation axis in some common molecules. The water molecule. Let me take the water molecule. Say, when you try to find out the proper rotation axis, you try the rotation in all the three mutually perpendicular axes. This is one axis. This is a symmetry operation. Then this can be rotated about this axis. This is not a symmetry operation. Then what about this rotation about this axis? This is also not symmetry operation. So the conclusion is there is only one proper rotation axis, SE2 axis. I don't take it for granted. I try the rotation about the other axis also. Then I decide that there is only one proper rotation axis, SE2 axis. Then The C2 axis is in the plane of the molecule. This has got a lot of significance. See, this is the plane of the molecule. Now the C2 axis is this. This is in the plane of the molecule. This is perpendicular to the plane. This is. So the C2 axis is in the plane of the molecule. Now boron trifluoride. This is the boron trifluoride molecule. Then the shape. This is plane or triangular. This is plane or the triangular. The boron and the three fluorine atoms are in the same plane. And this plane is called the molecular the plane. Now, it's got one C3 axis. And to illustrate the C3 axis, I hold it like this, not like this. Like this I hold. And if I hold it like this, in diagram, it will look like this. This bond is pointing towards me, which is the wedge bond. This is pointing away from me, which is hash bond. This is in the plane here. And this is the C3 axis. Then you try to describe the C3 axis. The C3 axis passes through what? The boron atom and perpendicular to the plane of the molecule. This is passes through the boron atom and perpendicular to plane. So this axis is perpendicular to that. So some axis will be in the plane, some axis will be perpendicular. So this is perpendicular to the plane. Then I try the other. See, I hold the molecule like this and rotate about this axis. I get this. So this is a proper rotation axis, C2. This is the second C2, this is the third C2. They can be represented like this. There are three C2 axes. Now we describe the C2 axis. Each C2 axis passes through the boron atom and one of the fluorine atom. This is how you explain it in words. And what about these? Are they in the plane or perpendicular to the plane? They are in the plane. The three C2 axes are in the molecular plane. This is what I want you to really, concerned about. You must know where exactly the proper rotation axes are present and whether these proper rotation axes are perpendicular or in the plane of the molecule. The lack of understanding these concepts is what makes the study of the group theory very difficult. Then ammonia molecule. This is the ammonia molecule. You try to, this is pyramidal. So ammonia molecule is pyramidal shape with the nitrogen atom at the apex. Okay. Now I'm going to try all this. First, I'm going to rotate it about an axis passing through the nitrogen and the center of the triangle formed by the three. Then I rotate it. You tell me whether this is a symmetry operation or not. That's a symmetry operation. So the C3 axis is there. Now, this is a pyramidal. Okay? See, suppose I consider this. If I rotate about this axis, what will happen? These two will come up. So this is not a symmetry operation. So there is only one proper rotation axis, a C3 axis. The C3 axis passes through the nitrogen and the center of the triangular base formed by the three hydrogen atoms. Now PtCl4, the 2 minus ion. This is the PtCl4 2 minus ion, which I can hold like this. Or like this. This diagram corresponds to this orientation. I'm holding like this in the plane. Or I can hold like this. Now, you identify or guess the proper rotation axis. What about this axis? Is it rotation axis or not? This is This is the C4 axis. This is the C4 axis. Diagrammatically, it will be like this. Okay? These two chlorine atoms are pointing towards me. Two are pointing away me. So these two are pointing towards us. These are pointing away. This is in the plane. The C4 axis passes through the platinum atom and perpendicular to the plane of the molecule. Then there are the four C2 axes separated into two sets. See, hold the molecule like this. This is a C2, right? This is a C2. This is a C2. Then this is a C2. This is a C2. But not all these C2 axes are identical. They are separated into two sets. Look at this diagram. So the green coded and the red coded. The green coded 2C2 prime axis. Red coded 2C2. Now you try, explain the C2 prime axis. The C2 prime axis passes through what? All the four are in the plane of the molecule. The C2 prime axis passes through the platinum atom and the two diagonal chlorine atom. Whereas the C2 double prime passes through the platinum and bisects the chlorine, platinum, chlorine bond angle. Repeat it. There are four C2 axes separated into two sets. These are the four C2 axes, two C2 prime axes, and the two C2 double prime axes. The four C2 axes are in the plane. All the four are in the plane. Then the C2 prime passes through the platinum atom and the two diagonal chlorine atoms, and the C2 double prime passes through the platinum atom and bisects the chlorine platinum. This. Now cyclopentadienyl anion. There is what? A C5 and how many C2s? 5 C2s. One C5 axis perpendicular to the molecular plane. Then 5 C2 axis all in the molecular plane. Can you describe the location of the C2 axis? How do you describe that? It passes through one corner and bisects the opposite side. Now, benzene. You guess. It has got a 1 C6, 6 C2 axis, which may be separated into two types, 3 C2 axis of one type, and you visualize these proper rotation axes of benzene ring. This is an assignment or exercise for you. You visualize these. Now, the symmetry operations associated with various symmetry elements. This is a very, very important aspect of this discussion of the group theory. Symmetry operation associated with symmetry elements. An important note. In the application of the group theory to molecular symmetry, we use the mathematical groups which have members. These members are called the elements of the group. Okay? We've got a group. The groups will have the members. These members are called the elements. These elements are different from the symmetry elements. And in the application of the group theory to molecular symmetry, the elements of the group are the symmetry operations and not the symmetry elements. The elements of the group may be symmetry element or the symmetry operation. According to the statement, the elements of the group are the symmetry operations and the symmetry element. Now it is getting more and more complicated. The elements of the group are the symmetry operation. So, more important than the symmetry elements of the symmetry operation. That's why I spend so much time to explain the symmetry operations associated with the CN. And without knowing that, we cannot proceed further. So, elements of the group are the symmetry operation. So, it is very important to be familiar with the symmetry operation associated with an E-symmetry element. We have already seen that identity E can generate only one operation, namely identity. Note down this. Now we shall consider the symmetry operation associated with the CN axis. Symmetry operation associated with the proper rotation axis. Follow this carefully. You consider the following symmetry operation. The boron trifluoride molecule planar is rotated through 120 degree in the clockwise direction. The three fluorine atoms are labeled 1, 2, and 3. When I rotate it through 120 degree, 1, 2, 3 will become 1, 2, 3 because this 1 will come here. And if you rotate it 120, this 1 will come here, then 2, 3. Then if you rotate it by 120, this is 3, 1, 2, then further rotation you will get. This will become, this is 1, this 1 will come here, 2 will come here, 3 will come here. Now, there are how many configurations? 5 configurations. Let me label these configurations. 1, 2, 3, 4, and 5. Now you will know why I was spending time in explaining distinguishable configuration and indistinguishable configuration. The identical and equivalent configuration, you will understand this. Had I taken up this straight away, you won't be able to understand, appreciate what I am telling here. Now you will be able to fully understand and appreciate what I am going to tell you. Now, this is C3 once. So you write it as C3. This is C3 operation carried twice. You call it C3 2. This is C3 3 times, C3 3. This is C3 4. Okay? Now, you compare the configurations 1 and 4 and tell me whether these configurations are equivalent or identical. They are equivalent or identical. They are identical. So this is C33 is identity. Now the 1 and 2 equivalent. Then the 1 and 2 is equivalent. Then 1 and 3 are equivalent, but 1 and 4 are identical. So these are two unique operations. C3 and C32 are unique operation, but C33 is equal to identity. Now, count the number of times the C3 operation is carried out before you arrive at this identity operation. Count the number of times the C3 operation is carried out before you arrive at the identity operation. How many times? This is 1, 2, 3rd. You get the identity. Our C3 are the unique and the C33. Therefore, the three operations generated by C3 axis are C3, C32, and E. So the three operations generated by, put it in your memory. The three operations generated by identity can generate only one operation, whereas C3 can generate the three operations. Now, you compare the configuration 2 and the configuration 5. 1, this is 1, 3, 3, 2. So these two configurations are identical. So I can say the C34 is C3. C34 is C3. So C34 is C3, then C35 will be C32. C36 is equal to C33, which is identity. Now, I'm going to teach you an important skill. The skill of simplifying the symmetry operation. Identity, symmetry operation, only one notation, identity. Here, there is C31, C32, C33, C34, C35, etc. Now, look at each of these. There is a subscript and a superscript. and the superscript is greater than the subscript. This is 4, 5, 6. The subscripts, 3 in all. And whenever the superscript is greater than the subscript, to simplify that, you simply subtract subscript from the superscript. So C34 will be C31, which is C3. And the C35 will be C35 minus 3, which is C32. This will be. What about C37? That will be C34, which will be C3. And so on. Then, if the superscript is greater than the subscript, subtract the superscript from the subscript from the superscript. You write down this, put it in your memory. This is a tool which you will be using frequently in simplifying the symmetry operation. The lack of understanding of these concepts is what is going to make the group theory a tough topic. Now, C3 can generate 3 operations. The C4 can generate 4 operations. C5 can generate 5 operations. C6 can generate 6 operations. In general, a Cn axis can generate n operation, namely Cn, Cn2, Cn3, up to Cn. Note down this. A Cn operation can generate n operations. Cn axis can generate n operations. Identity can generate only 1 operation. Also, the Cn n is equal to identity, whether n is odd or even. Cn n is equal to identity, whether n is odd or even. That is C3 3 is identity. C4 4 is also identity. Now Cn n plus 1. What will be that? Subtract n from the n plus 1, that is Cn. Then Cn n plus 2. N plus 2 minus n, that will be C2 and so on. Now, operation generated by some common Cn axis. This exercise is a very, very important exercise. You have to be very, this is something like learning to ride a cycle. You learn a technique here. Then, once you know a technique, you can extend that technique to a similar situation. C2 axis. A Cn axis can generate n operation. A C2 axis can generate how many operations? The 2 operations, right? This is C2 and C22, which is identity. Then C3 axis can generate how many operations? 3 operations.
3 operations.
Yeah, 3, that is C3, C3 2, and the C3 3, which is identity. Now C3, C4. How many operations? You can tell me.
4
operations.
operations.
That's good. Now, what are the 4 operations?
C4,
Uh,
C4 2, C4 3,
C4, that's all. Okay? You learn
and E.
to ride one cycle. You can ride all cycles. Now, let me consider the C42. Okay? C42, this stands for rotation through 90 degree twice. That is 90 into 2, which is 180 degree, which is same as rotation through what? 180 degree once. If the rotation is through 180 degree once, that is C2. So I can conclude that C42 is equal to C2. Now, I have a different situation. Earlier, we found the operation like C35, C34, C36, etc., where the superscript was greater than the subscript. Here, the superscript is less than the subscript. In such situations, to simplify this, you divide both superscript and subscript by a common factor. Here the common factor is 2, so this is C2. You know down this. If the superscript is less than, no textbook gives these things on this. This is what the tool I use in my teaching. If the superscript is less than the subscript, divide both by the common factor. So therefore, the 4 operations C4 are, you write the C4, then instead of the C42, you write the C2, then C43, and the C44, which is identity. Then then you can verify this diagrammatically. Then the four operations of the C4 axis are C4, C2, C43, and C4. Now, this set of operations includes C2 and identity. Which are the operations generated by the C2? So the C4 axis, or the four operations of the C4 axis, include the two operations of the C2 also. This means that the C4 axis is also a C2 axis. You can verify this diagrammatically. The C4 axis in the PTCl4 is also a C2 axis. In other words, C4 axis is coincident with the C2 axis. Then C5 axis. How many operations? 5 operations. C5, C5-2, C5-3, C5-4, and C5-5. These operations cannot be written in any other form. Just leave them like that. Then C6 axis. How many operations? Can anyone answer me?
6 operations.
What are the 6 operations?
C6, C6,
Uh,
2,
uh,
that is C3.
yeah, I will come to that later. You just
Okay,
list
fine.
that. Yeah.
C6, C6, 2, C6, 3,
Uh,
C6, 4, C6, 5, and C6, 6.
yeah. Let me write down this. These are this. Now you can do your simplification. C6 is C6. Then C6
C6, 2
is
is C3.
C3. Okay? Then C63 is C63 is
C2.
C2. Then C64 is
C64 is C3 twice.
twice. Then C65, then C66. So the 6 operations are what? C6. You don't mug up these things, right? You just learn the strategy. There are 6 operations. Then to simplify that, you learn the basic concepts, which you already learned. That's why he said, the more you learn, the easier it will become. I taught you only how to write the symmetry operation associated with the C2. You are able to write out symmetry operation. This is a skill which is needed by the students and teachers of the group theory. Now we can verify this diagrammatically. Now the 6 operations of the C6 axis are this. Now the C3, the C3-2 and identity are operations of the C3. What does it mean? The C6 axis is coincident with what? The C3 axis, or that means C6 axis also is C3 axis. In other words, C6 axis coincident with C3 axis. In general, so if you had C4, we have a C2. If you have C6, we have a C3. In general, if an even order Cn axis exists, then C n by 2 axis should exist independently. Now, these operations include C2 and E, which are the operations generated by the C2 axis. So the C6 is coincident with the C2 axis also. You draw the diagram of benzene molecule and check whether the C6 is also a C3. The C6 is also a C2. Then you will have a full understanding of the various rotational axes present in the benzene molecule. Now, that's the end of the first presentation. The next presentation is symmetry, about symmetry elements and the symmetry operation part 2. In this, we'll discuss about the mirror plane and the inversion, the center